Surface water is an important part of the hydrogeologic system, and we definitely want to have this as one of the things that we can analyze and measure in the field. If we take a look at a water balance on a stream, we'll get something like this. We just have a very idealized stream reach here. And we've got a volumetric flow in the stream, and we might expect the volumetric flow or the velocity to vary over the cross-section of the stream. There will be some kind of a total volumetric flow that's coming into this reach and a total volumetric flow that's coming out. And we might also expect there to be some groundwater that flows into this reach. And so we've got some flux of groundwater coming into it, and so the volumetric flow rate that's coming out is going to be equal to the volumetric flow rate that's coming in plus the amount of groundwater flux that has entered over this reach. So we want to be able to measure those things as part of characterizing the stream. So the USGS has a network of gauging stations where they measure the flow rate in streams, and this is a valuable resource for hydrogeologists. You can, in many cases, find a stream gauging station fairly close to where you are and use that to obtain data that can be very helpful. This is a map of the gauging stations where there are real-time data. There are about 7,000 of these, and there are about 11,000 total stations where some data are available. Some of the gauging stations are put out of service, usually as a result of budget cuts. So not all of the ones where data are available are currently in operation. The way these gauging stations work is that there's instrumentation set up to measure the stage of the stream. The stage is the water level, and as it turns out, we want to know what the flow is, but it's fairly tricky to measure the flow with instrumentation, but it's pretty easy to measure the stage. So what you do is measure the stage and then correlate the stage to what the volumetric flow rate is. And the way that that's done is to have instrumentation set up that's designed to measure stage. And the water level in the stream, it's going to fluctuate. It'll fluctuate just due to waves and turbulent action. And so in order to make a good measurement, typically what's done is to use a stilling well that's set off back away from the stream and connected to the stream through a tube shown here. And as a result, the water level in the stilling well only varies slightly. And so we can measure the water level here, and the average water level here will be equal to the average water level in the stream. So instrumentation is set up in this stilling well to measure its level. And what's shown here is just a simple float system. You can imagine you have a float that goes up and over a pulley and a counterweight here. And then as the water level goes up and down, that turns a wheel here and registers the water level. And so that's an old style of water level measurement system. Many of those were set up. There's one over near Pickens that until recently was set up and measured water levels that way. The more recent setups use electronic transducers and various other types of electronic instrumentation to measure the water level. Many of these systems are set up with satellite telemetry or cell phone telemetry, and so they've got a data link here. It sends out the data and sends it back to the USGS home base, and it's available on the internet soon after it's recorded. So if you want to get the stage and the flow of your favorite stream, and there's a gauging station on it, you can look it up on the internet and get the data. It's usually posted every 15 minutes, so it's pretty close to real time. So this is how stage is measured, but what we're really interested in is the discharge. So the way it works is that you measure the stage, and then you send somebody out, and at a particular stage the person goes out and measures what the discharge is in the stream. Usually that requires a person to go out and make the measurement by hand using stream gauging techniques that I'll tell you about in just a second. And so you go out there and you go out at, say, a low stage, and you measure a fairly low flow, and you get a data point right there. And then you go out and it's a bit higher stage and a bit higher flow, and you get another data point. And you go a little bit higher stage and you get that data point, and you get a couple more data points, and so you have these data then, and you connect them with a curve, and that's a stream rating curve. That allows you to correlate the stage and the discharge. So ultimately we want to use this then to allow us to take measurements of stage and calculate what the discharge is at that stage. So there are two USGS gauging stations close to Clemson, and one of them is on 12 Mile Creek, the other is on 18 Mile Creek. And here's an example of some of the data from the one on 12 Mile Creek. This header here shows that the gauge height, or the stage of the stream, the discharge, the volumetric flow rate, and precipitation are all available from this site. This is a plot of the gauge height as a function of time from May till early June in 2010. So this would have been during field camp 4 years ago. And you can see the stage is around 2 feet until we get a storm here, and it rises from May 30th to right early in June. On June 1st, it rises from around 2 feet to almost 3 feet in stage, and then it falls off pretty quickly. We can also get data for the discharge. So we apply the stream rating curve, and we get discharge as a function of time. And this is for a little bit later period than these data. And we just see the discharge now. This is right here, that's 90 CFS, cubic feet per second. And so that's kind of a base level, and it jumps up here during this rainstorm from 90 to 120, and then here's a bit bigger rainstorm, and it goes up to 180 cubic feet per second. So the flow rate doubles from here to here. This gauging station has been in operation for 29 years, and so that data set, typically it's daily data that's measured and stored, and so that daily data set of 29 years of data can be used to calculate statistics of the flow. And here's a sampling of some of those flow statistics, and this is all available on the website. So you can find this site pretty easily. If you just Google USGS stream gauging, you'll get a site that has a map like this. And then if you click on South Carolina, and we're right up here in the western part of South Carolina, and you can just locate the stream that you want. The gauging station that is located there as a dot, and it'll take you right to it. So I would try that. Try finding the 12 Mile Creek gauging station, and also the 18 Mile Creek gauging station. Here's some data from the 12 Mile Creek. This isn't the whole data set, but this shows you several years of data from 2005 to 2009. These are daily data, and you can see that there's quite a lot of fluctuations. These are some pretty big flooding events, and you can see this is the base flow level, and you can see that it's generally decreasing during this time period. Here's another period of decreasing base flow, another period of decreasing base flow. These are called base flow recessions. And so in general, this kind of long-term record consists of periods where the base flow is in recession, and it's generally decreasing, although there are a couple of storms here and there during the recession. And then the rainfall starts to pick up, and there's a period of recharge here. and that's where the aquifer is being recharged, and the base flow is generally increasing during this period. Okay, so we're also interested in the velocity distribution. This is going to be something we need to be aware of and be able to measure in order to determine the total volumetric flow. So here's some data. Let's look at this one in particular. This is a cross-section through a stream. So if the channel is like this, this is a cross-section through it like that. And so the velocity is perpendicular to this surface. And the color is the velocity. This is done with a specialized flow meter, a Doppler flow meter that can measure with very high resolution. And so you can see that the maximum velocity is right about here, and the minimum velocity that's measured is down here on the bottom. It can't measure all the way to the bottom, but it's generally this high velocity here near the surface, kind of in the middle, but it's really off to sort of near the deep side, and then lower at depth. This shows some velocity profiles, and you can see that it's pretty similar and has a general shape that looks like that, although we don't really know what it looks like right down close to the bottom. What is expected is that where you have a fairly firm stream bottom, that the velocity goes down like this, and that the velocity at the stream bed is 0. And then this is a longitudinal profile. So this is one bank here, and this is another bank somewhere over here, and this is the velocity as a function of the width along the river. And so you can see once in the middle of the river, the velocity is fairly similar, and then it tapers off towards the banks. And it's not quite clear from these data just where the bank is, but you might expect it as you approach the bank, it would also drop off, and it's probably going to be going, well, it'll go to 0 right at the very edge of the river. Okay, so there's a longitudinal profile. So what we need to do is take this kind of velocity distribution into consideration when we measure what the total volumetric flow is. So here's kind of the mathematical version of how we determine the volumetric flow. So if we want to get technical about it, the volumetric flow is going to be the velocity that's perpendicular to a cross-section integrated over that cross-sectional area as we've shown here. Okay, so that's the way to write it mathematically. What we can do is say, well, we're integrating the velocity over this area. Okay, that's formally what we need to do to get what the volumetric rate is. And so the way that we do that, though, is to break down this double integral, which is a little bit cumbersome. But if we break that down, we can set it up in a way that makes it fairly straightforward to solve. So this double integral can be written like this, where instead of just integrating it arbitrarily over this area, we integrate from 0 to d the velocity with respect to dz. So we're integrating from the z is the vertical coordinate, and we're integrating that from 0 to d, which is the depth. And we're integrating the y coordinate, which is the width. So we would have a coordinate system that would be like this. So this is y, and that's z. Okay, so we're integrating the velocity with respect to z and y. All right, so that's another way to look at it. But what we can do is say, well, this thing here, if we integrate, if we look at what that is, that's the depth. The depth times the average velocity. Okay, that integral we can recognize that as depth times average velocity. Okay, so then we can just substitute in for this block the water depth times the average velocity. And we're going to then integrate that across the width of the stream. Okay, well, when we integrate something, we can, this is like determining the area, so we can break it down into some intervals and add them up. And so we can take this integral and turn it into a sum. So that's what we've done. And we're going to take this thing, which is a formal integral, and we're going to say, well, I'm going to approximate that by taking the depth, the average velocity, and a little incremental width. So if I do that, then I will get an incremental velocity or incremental volumetric flow rate, and then I add them all up and I get the total flow rate. Okay, so here's the way it's going to work. We're going to take the cross section here and we're going to divide it up into blocks. So I've showed one shaded block here. And what we need to do is determine the volumetric flow rate through that block. That's going to be the average velocity there times the width of the block times the average depth, d1. Okay, and so if I can, for sure I can measure the average depth and the width, and then if I can measure the average velocity within that orange block, then I can determine the flow rate within that block. So that'll give me Q1. And then if I repeat it here, I get Q2 and Q3, Q4, and so on. Okay, so I divide the stream cross section up into these blocks that are defined by a width and an average depth, and then I determine the average velocity within that block. That gives me a series of volumetric flows, and then I add them up. So that's what I mean by this. Okay, so we start with this thing. It's a formal integral. That's formally correct, but what we do is go through a series of steps that makes this, basically turns this integral into something that we can deal with in the field, and that's this guy. We're determining the volumetric flow rate through each one of these small little pieces and then adding them up. Okay, so let's take a look. Here's this process underway. This is on 18 Mile Creek, and this guy's using a seepage or a current meter to measure the velocity at that point. And the stream has been divided up into various increments, and so we're getting the velocity, average velocity within that cross-sectional area. We get the average depth, and we got the width. Okay, and so make that measurement, and then move on to the next width increment. So what we have to do is divide the stream into increments, and if the flow in the stream is fairly uniform, then you could use uniform increments. If there are places within the stream where the velocity is particularly fast and ones where it's slower, then you might want to make uneven increments where the width increments are closer where the velocity is fast. So that's the idea going on right here. And each increment would be, say, around 5% of the flow. That's some guidelines. Probably between 5 and 10%, I would say, of the total flow. So you want to take the width of the stream and divide it into at least 10 increments, and probably 20 would be better. And so then you get the increments, and you could make them, you could select how the increments are distributed based on the current, but you could also, at least as a first cut, just make the increments even. Okay, so you've got width increments, and you can measure the depth. And so now we need to measure what the average velocity is. So we can use a current meter to measure the velocity, and we saw in the slide where the velocity was measured in some detail that the velocity differs as a function of depth. And this has been looked at many times, and what often occurs is that the velocity distribution here is pretty close to a parabola. You know, if I were to extend this up like that, that would be the shape of a parabola. Okay, and so if it's parabolic, then you can get the characteristics of a parabola, and from that you can determine that the average velocity, right there, that green arrow, that's the average velocity over this entire depth. And that average velocity is equal to the average velocity is equal to the true velocity at a depth of 60% of the total depth. So if you measure the total depth and you take 60% of that and you measure the velocity right at that depth, that equals the average velocity, assuming everything's behaving themselves. There are a variety of other ways of doing this where you make additional velocity measurements. Some involve making a measurement at 80% and 20% depth and using those data. I posted a reference that talks about stream gauging in some detail, and it describes these other more detailed methods. But we're just going to use the 6/10 measurement for now. And so what we say is that the average flow rate, this green line, if we take that and multiply it by the depth, then we get the same total volumetric flow rate as if we have this parabolic flow. Okay, so that's going to be one method for determining the average velocity, and this is the way we'll do it when we have a current meter to make this measurement. This is the kind of current meter that we'll use. This is a Pygmy meter, and it has these small cups that spin around, and you measure then the rate at which it spins. Each time it revolves around once, it makes a click. So you wear some headphones. You can see this guy here has headphones on, and he's listening for these clicks. He counts the clicks, and then you take the number of clicks per unit of time, clicks per minute, and that then correlates to the flow rate. And there's a little table that does that correlation. So there are other ways to do this. Here's a larger current meter, larger than a Pygmy, although it has the same kind of rotating cups, and it's on this weight, and this thing is being lowered off a bridge. So if you're just working in a small stream and the flow is fairly mellow, then you can just wade in the stream and do it like this. But if the water's deep, or if it's fast, then it's just not safe to do this. And so what's done is to, in this case, they're lowering this off the bridge. There are other contraptions where they stretch a cable across the stream and lower it off the cable. Sometimes they have a person that is dangling from the cable and lowering the stream gauging instrumentation off of the cable. I would recommend looking at the USGS website that describes this. They have some pretty interesting arrangements. But we'll just use a Pygmy meter, and we'll go into the stream, wade into the stream, and make the measurements of the average velocity at 6/10 depth. So here's what I just described. In some cases, though, you can't really use a current meter. Maybe you don't have the current meter, or the water depth might be really too shallow to use. And so if that's the case, then what you can do is measure the velocity of the water surface. And you do this by measuring the velocity of something that's floating on the surface of the water. One thing that's used, that's what's being shown here, is this is supposed to be an orange. So if the water's deep enough, you can float an orange in there. An orange will float, but it'll float just right close to the surface of the water, and so you won't have the wind blowing it around. And you have two points along the stream, and you time how long it goes from point A to point B. And if you know the distance between point A and point B, then you can get the velocity. And if you have a parabolic velocity distribution, the velocity at the surface is 90% of the average velocity. Or I'm sorry, I got that backwards. The average velocity is 90% of the velocity at the surface. The velocity of the surface is going to be the maximum velocity. So if you measure that, multiply by 0.9, then you get an estimate of the average velocity. So this is not going to be as accurate as a current meter, but you would be surprised. This can be remarkably accurate, and it's pretty easy to do, and it's also something that can be done if you don't happen to have a current meter handy. So we'll try both this method with the Pygmy meter and this method with, well, you could use an orange or you could use other things that are convenient. So this is a close-up of a Pygmy meter. When you use this, it'll be set up with a travel pin, a brass pin that is right here. And so there'll be a set screw in the side of the instrument. You loosen the set screw and carefully remove the travel pin, and then put in it'll be made of brass, and then you put in a chrome-plated pin. Then attach the wire and headphones. Put in the chrome-plated pin, and then make sure to secure the set screw so the chrome-plated pin doesn't fall out. You also secure the instrument on with that set screw. Attach wire and headphones. Adjust the vertical position so it's at 6/10 depths. Point it upstream, count the number of clicks per unit of time, and then use a chart to convert the revolutions to velocity. So I made a video that describes this process and shows you in some detail about what to do. So check that video out before you do the stream gauging. Yeah, and so this thing is quite delicate, and it's a precision instrument, and it's fairly expensive, so please be careful with it. The staff that is used with the Pygmy meter is set up to measure, to allow you to set the meter at a 6/10 depth position in a convenient way. So take a look at the video that describes this. It goes into, I think, enough detail so you'll be able to understand quite well how to do it. Okay, so this is another look at how to set up the calculations, and it's dividing the stream up into different intervals, width intervals, and it's determining the depth and the velocity. What it's doing is also calculating this gives you a scheme for calculating the average depth over a certain width. So this gives you an approach for setting up the calculations. There's a third way that I want to talk about for measuring velocities. This is with a pitot tube. And pitot tubes, you may have seen these on airplanes. That's what it looks like. It's this little pointy thing that's about 6 inches long there, and it's pointing into the direction of flow, pointing forward on an airplane. And this is used to measure the velocity of air flowing on an airplane, but it'll also work in a stream. And the way that it works is that if you have, well, this is a cutaway, and so there's a tube, there's an opening that goes right down the center, and that opening goes to here, and there's another opening that goes right here in the side, and that connects to this reservoir here. And so when you have flow, the hydraulic head that is felt right here is it's the total hydraulic head. So it's pressure head plus elevation head plus v squared over 2g. That's what's felt in this center tube here. In the side tube, though, because it's perpendicular to the flow, it doesn't have any velocity effect. So the head right there is only, let's call this head 1, right there. Head at point 2 is just the pressure plus z. So this and this are the same. So the difference between H2 and H1 is that. Okay, so this is this pitot tube, and you can buy them, but you could also just make one if you have two pieces of tubing and you hold them in a cross like this, and the flow is going like so. And so this tube is pointed into the flow, and this is perpendicular to it. Then this one feels the total head here with the velocity head, and this one feels the velocity head is 0. And so what you do is hook this thing up, these two tubes, up to a manometer, and the manometer, which I'll talk about here in just a second, allows you to measure the head difference between these two tubes, and the head difference will be equal to this. Okay, and so if you know what that head difference is, you know what g is, you can solve for velocity. Okay, so that's how a pitot tube works, and we'll use one to measure the flow rate. We'll actually use tubing set up like this, so you can get an idea about how the pitot tube works, and it actually ends up being remarkably accurate.